Module 7, Lecture B, Training Networks. By the end of this lecture, you will be able to explain gradient descent, stochastic gradient descent, and backpropagation at an intuitive level. Implement a small neural network training loop from scratch using NumPy, and evaluate neural network performance and identify signs of overfitting. Learning mechanics. Gradient descent basics. Gradient descent is a core method neural networks use to learn. The network starts with weights and biases that may produce poor predictions, then measures its error and adjusts those settings to reduce it. Like moving downhill in fog by sensing the slope, gradient descent takes small steps that guide the parameters toward lower error. The gradient shows how each weight affects the network's error and indicates which direction to adjust it to reduce loss. Gradient descent uses this information to update parameters, while the learning rate controls how large each update is. If the learning rate is too small, training is slow. If it is too large, the network may overshoot good solutions. Gradient descent is an iterative process that improves a network over time. The network makes predictions, the loss function measures the error, and the parameters are adjusted to reduce that error. In complex real-world problems, it may not find the absolute best solution, but it usually finds one that works well enough. Python code. Gradient descent basics. Gradient descent updates a parameter step by step to reduce prediction error. The loss measures that error before each update, and the learning rate controls how large each downhill step is. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting tools to visualize results, such as how loss changes during gradient descent. We begin with a small civil engineering dataset for gradient descent. It pairs load values in kips, or thousands of pounds, with corresponding settlement measurements in inches. The data is stored as floating point arrays to support accurate calculations. Before processing, confirm that the load and settlement data are both one-dimensional and have the same number of values. This ensures each load matches one settlement value and helps prevent errors caused by inconsistent data. Before using gradient descent, the load and settlement data are scaled by dividing each set by its maximum value. This normalizes both inputs to a range from 0 to 1, reducing large differences in scale and helping the optimization process take more stable steps. We start gradient descent with a deliberately poor weight estimate of 0.1, so the model has room to improve. The learning rate is set to 0.4, which controls how large each update step is as the loss is minimized, balancing speed with stability. We create two empty lists to record loss values and weight values during gradient descent. These records help show how the loss decreases and how the weight changes across iterations. The loop runs 25 gradient descent steps. At each step, the model uses the current weight and scaled inputs to predict settlements, then compares those predictions with the actual scaled values. The difference gives the error, showing how far the model is from the data at that point. The code first measures prediction error by averaging the squared differences between predictions and actual values. It then calculates the gradient from the errors and input values, showing how the weight should change to reduce the loss during gradient descent. The code updates the weight by moving it in the direction that reduces prediction error using the learning rate and gradient. It then records the current loss to track error over time and saves the updated weight to show how the slope estimate changes across iterations. After training, The learned slope is converted from scaled values back to the original units of inches per kip by adjusting it using the maximum settlement and maximum load. This gives the settlement expected for each unit of load in the original measurements. The final loss is then taken from the training history to show the model's ending mean square error and overall fit. The output reports the NumPy version for reproducibility, then compares the initial and final loss values to show how gradient descent reduced prediction error. It also prints the learned slope, which describes the relationship between load and settlement in inches per kip. Together, these results demonstrate that training successfully improved the model's fit. This plot shows how the mean squared error changes during gradient descent. It graphs the loss history across each step, using clear markers, labels, a title, and a light grid to make the trend easy to read. The main purpose is to confirm visually that the loss decreases as the parameter moves downhill. This script uses gradient descent to improve a simple linear model that predicts settlement from load. After scaling the data and starting with an initial slope, it repeatedly updates the slope to reduce mean squared error, with the learning rate controlling the size of each update. Over 25 iterations, the loss decreases, showing that the model's predictions are improving. The final results report the starting and ending loss, the learned slope, and a plot of the loss reduction. Stochastic gradient descent. Stochastic gradient descent is a faster practical version of gradient descent used to train neural networks on large datasets. Instead of using the full dataset for each update, it adjusts the model with one example or a small batch at a time. These updates are noisy because they use limited information, but over many steps, they help reduce loss and improve predictions. Stochastic gradient descent trains neural networks more efficiently by updating the model using small batches of data instead of the full dataset at once. This makes training faster, especially for large datasets that may not fit in memory. It also works well with modern hardware while still providing useful updates for learning. The randomness in stochastic gradient descent can be useful because it helps the model avoid getting stuck in poor solutions. Its noisy updates let the model explore different weight settings before settling. However, performance depends on careful tuning. A learning rate that is too large can cause unstable jumps, while one that is too small slows learning. Batch size also matters, since very small batches add too much noise, and very large batches behave more like full gradient descent. Python code, stochastic gradient descent. This script compares batch descent and stochastic descent using a small, concrete dataset, so the mechanics are easy to see. The example is set in civil engineering, using beam deflection data to show how the two optimization approaches work in practice. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting module to create visualizations, helping us graph results and understand data trends. We set a fixed seed for NumPy's default random number generator, so stochastic gradient descent makes the same random selections each time the code runs. Using the seed value 7 makes results repeatable, which helps with debugging and comparing runs. We generate synthetic beam load data by creating 40 load values from 10 to 80 kilonewtons. The true deflection is modeled as a simple linear relationship, with deflection equal to 0.42 times the load plus 1.5 millimeters. To make the data more realistic, random normally distributed noise with mean 0 and standard deviation 1.8 is added to the deflection values. This step creates a deflection dataset in millimeters by combining calculated beam deflection values with random noise. The added noise represents measurement error or real-world variability, making the data more realistic. To standardize the load data, first find the average load and how much the loads vary around it. Then adjust each load by subtracting the average and dividing by the standard deviation. This gives the data a mean of 0 and a standard deviation of 1, which supports more stable optimization. Before running gradient descent, confirm that the standardized load values and deflection measurements have matching shapes, so each load pairs with one measurement. Also verify that both arrays are one-dimensional, since the calculations assume this structure and may fail if the data has a different shape. This function measures prediction accuracy using mean squared error. It first makes predictions with a linear model, then compares them with the actual values. By averaging the squared differences, it returns one number that shows how far off the predictions are on average. This function makes one gradient update using a small batch of data. It predicts values with the current weight and bias, compares them with the actual values to find the errors, and uses those errors to compute the weight gradient. That gradient shows how the weight should change to reduce future prediction error. In one gradient descent step, the bias gradient is found by taking twice the average error. The weight and bias are then adjusted by subtracting the learning rate times their respective gradients. The updated values are returned for the next step. For full batch gradient descent, the model begins with weights and bias set to 0. A loss history is kept to monitor learning during training, and the learning rate is set to 0.08 to control how large each optimization step is. This helps balance faster progress with stable convergence. The training loop runs for 60 gradient descent updates. In each step, the gradient step function uses the full dataset to adjust the weight and bias in the direction that lowers mean squared error, scaled by the learning rate. After each update, the new loss is calculated and stored, so we can track how the model's error decreases over time. Stochastic gradient descent begins by setting the model's weights and bias to 0 as a starting point. A loss history is also prepared to track how performance changes during training. Each update then uses a small random batch of 5 data points, making training faster but more variable than using the full dataset. The loop runs stochastic gradient descent for 60 iterations. In each iteration, it randomly selects a mini-match without repeated data points, uses it to update the model's weight and bias with the chosen learning rate, and carries those updated values forward. After each update, it computes the mean squared error on the full dataset and stores it, so we can track how the model improves over time. The code reports the NumPy version to support reproducibility, then shows the final loss for both full batch gradient descent and mini-batch stochastic gradient descent. These values make it easy to compare the two optimization methods. It also notes that stochastic gradient descent is usually noisier, but can often move toward lower loss quickly. A new plot is created to compare how loss changes during training. It shows the loss from full batch gradient descent, where each update uses the entire dataset, alongside the loss from mini-batch stochastic gradient descent, where updates use smaller random subsets. This comparison highlights how the two methods reduce error and converge differently over time. The plot tracks training progress by showing update steps on the horizontal axis and mean squared error on the vertical axis. Its title emphasizes that many small, noisy stochastic gradient descent steps can still reduce loss effectively. A legend is added to distinguish the full batch and mini-batch gradient descent curves. To finish the visualization, the tight layout function adjusts spacing so the plot elements fit cleanly. Then the plot is displayed, making it possible to compare the loss paths of full batch gradient descent and mini-batch stochastic gradient descent. This script compares full batch gradient descent with mini-batch stochastic gradient descent using noisy synthetic beam deflection data. Both methods train a simple linear model to reduce mean squared error by updating weights and bias. Full batch training gives a smoother loss curve, while stochastic training is noisier but can drop faster through many small updates. The final losses and plot show how both approaches reduce error effectively. Backpropagation basics. Backpropagation helps a neural network learn by measuring how far its prediction is from the correct answer, and then tracing the error backward through the layers. It identifies which weights and biases contributed to the mistake, and guides how they should be adjusted. In this way, the network gradually improves its future predictions. Backpropagation measures how much each network parameter contributes to the final error. It starts at the output and moves backward through the layers, using each layer's influence on the next to assign responsibility for mistakes. This lets the network identify which connections need adjustment, even when their effects pass through many layers. Backpropagation calculates the gradients that tell optimization methods how to adjust a neural network's weights and biases. Parameters that contribute more to error are changed more strongly in the opposite direction, while less important ones change only slightly. Repeating prediction, error measurement, and adjustment helps turn an untrained network into a useful model. This makes backpropagation essential for deep learning because it updates many parameters efficiently. Python code, backpropagation basics. Backpropagation traces prediction error backward through a neural network to improve learning. This small NumPy example applies the idea to civil engineering data for predicting safe beam behavior. We start by importing NumPy to handle the numerical array operations needed for the neural network. We also import Matplotlib's plotting tools so we can later visualize the model's learning progress, such as by plotting the loss curve. We initialize NumPy's random number generator with a seed of 7, so it produces the same random sequence each time the code runs. This makes results repeatable, which is important for learning, testing, and debugging. We create 2 floating point arrays for a civil engineering example. One stores beam spans in feet, and the other stores applied loads in kips. Using floating point values helps keep later calculations precise. The span and load values are first combined into a 2-column matrix, with each row holding one paired observation. The data is then standardized by centering each column around 0 and scaling it to have a standard deviation of 1. This helps keep gradients stable and supports faster, more reliable training. The label array marks whether each beam's deflection behavior is acceptable. It contains 6 labels. The first 3 indicate acceptable behavior, and the last 3 indicate unacceptable behavior. A shape check confirms that the feature data has 6 rows and 2 columns, while the labels have 6 rows and 1 column, so the inputs and labels are properly aligned. A small 2-layer neural network is initialized by setting weights and biases for each layer. The first layer uses a randomly generated weight matrix to connect the inputs to the hidden layer, with its bias set to 0. The second layer similarly uses random weights to connect the hidden layer to the output, with a 0 bias. These starting values allow the network to begin learning by adjusting its weights and biases during training. The sigmoid function transforms an input into a value between 0 and 1, using 1 divided by 1 plus the exponential of the negative input. This makes it useful in neural networks, especially for binary classification, because it adds nonlinearity and produces probability-like outputs. Its derivative is also easy to compute, which helps during backpropagation. We create a list to record the loss after each training epoch, so we can monitor how the model's error changes over time. We also set the learning rate to 0.4, which controls how large each weight update is during gradient descent. The training loop runs for 120 epochs and begins each pass with a forward pass through the network. The input data is combined with the first layer's weights and bias, then passed through the sigmoid activation function to produce the first layer's activations. These activations are then combined with the second layer's weights and bias, and sigmoid is applied again to produce the network's predicted output. This prepares the model to measure error and update its weights through backpropagation. We measure prediction error using mean squared loss, which averages the squared differences between predictions and true labels. This loss shows how far the model's predictions are from the correct values. By saving each loss value, we can track how the error changes as the model learns. To backpropagate through the output layer, first find how the loss changes with the layer's pre-activation values by combining the prediction error with the sigmoid derivative. Then compute the second layer's weight gradient using the first layer's activations and this output gradient. The bias gradient is found by summing the output gradient across all samples while keeping the result in the correct two-dimensional shape. To backpropagate through the first layer, we first compute the hidden layer error by passing the output error backward through the second layer weights and scaling it by the hidden layer activation derivative. This distributes the output error to the hidden units. We then find the first layer weight gradient by combining the input data with this hidden error, and find the bias gradient by summing the hidden error across all samples while keeping the dimensions consistent. Gradient descent updates the neural network by adjusting each layer's weights and biases to reduce loss. For both the second and first layers, the current values are changed by subtracting the learning rate times their gradients. This moves the parameters opposite the gradient, helping the network gradually lower prediction error as it learns. The predicted probabilities are first flattened into a simple one-dimensional form. Each value is then converted into a binary prediction using a threshold of 0.5, where higher values become 1 and lower values become 0. Accuracy is calculated by comparing these predictions with the true labels and taking the proportion that match. The output reports the NumPy version for reproducibility, then compares the loss before and after training to show how much the model improved. It also gives the training accuracy as a percentage, indicating how often the model predicts the correct class. Backpropagation is used to compute gradients before each update, guiding the changes to the model's parameters. This plot shows how training loss changes over epochs during backpropagation. A clear line chart displays the mean squared loss, with labeled axes, a title, and a light grid for readability. By viewing the loss trend over time, we can assess whether the model is learning and reducing prediction error. This script shows how backpropagation trains a small two-layer neural network to predict beam behavior in civil engineering. It normalizes inputs such as span and load, then uses full batch gradient descent to reduce mean squared prediction error over 120 training cycles. As the weights and biases are updated, the loss decreases, showing that the model is learning. The final output reports the starting and ending loss, training accuracy, and a loss curve that confirms improved predictions over time. Training code. NumPy training loop. A NumPy training loop shows how a neural network learns by repeatedly improving its weights and biases. It starts with small random values, makes predictions, measures errors, computes how each parameter contributed to those errors, and updates the parameters to reduce future mistakes. Modern libraries automate this process, but NumPy makes the core cycle of prediction, evaluation, gradient calculation, and updating easier to see. A typical NumPy training loop repeatedly runs a forward pass to make predictions, computes the loss, and then runs a backward pass to calculate gradients. Each layer uses its current weights, biases, and activation function while saving needed intermediate values for backpropagation. The gradients are used to update the parameters, with the learning rate controlling how large each update is. Repeating this cycle gradually improves the model. When building a training loop in NumPy, focus on what happens in each iteration and how data shapes move through the network. Use vectorized operations to process many examples at once, either across the full dataset or in smaller batches. Track loss after each epoch to monitor learning and spot problems when progress stalls. This hands-on approach builds a strong understanding of training before moving to higher-level frameworks. Python code. NumPy training loop. Build a small neural network from scratch using NumPy for each training step. As it trains, track the loss so you can see whether the model is learning effectively. We import NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib pyplot to create plots for visualizing data and results. We set a seed for NumPy's default random number generator so the code produces the same results each time it runs. Using a fixed seed, such as 7, makes computations reproducible when randomness is involved, including tasks like neural network weight initialization or adding noise to data. A small civil engineering dataset is created by generating 80 evenly spaced load values from 5 to 80 kips and 80 span values from 10 to 60 feet. Each set is shaped as a column of data, representing two key features used to describe structural cases: load and span length. The load and span feature arrays are combined into one two-column design matrix, with each row representing a data point. The target values are then created from a simple linear relationship. Loads are weighted by 0.03, spans by 0.015, and the results are added together. This produces a target array that represents a weighted sum of the two features. Mild random noise is added to the target data to make it more realistic. The noise comes from a normal distribution centered at 0, with a small standard deviation of 0.08, and matches the target data's shape. This introduces slight measurement-like variation, similar to what occurs in real-world data. The input data is standardized by finding each feature's mean and standard deviation, then using them to center and scale the values. After this process, each feature has a mean of 0 and a standard deviation of 1. This helps make training more stable and supports smoother gradient descent. To make training easier, the target values are standardized before optimization. This means finding their mean and standard deviation, then centering the data and scaling it to unit variance. The result is target data that is better suited for gradient descent. The standardized data is split into training and validation sets, using the first 60 data points for training and the remaining points for validation. The same split is applied to the target values. This lets the model learn from one subset and be evaluated on separate, unseen data, to check how well it generalizes. Before running matrix operations, the code checks that the training features have 60 rows and 2 columns, and that the training targets have 60 rows and 1 column. These shake checks confirm the inputs and targets are aligned correctly for the neural network, and help prevent runtime errors from mismatched dimensions. We set up a small neural network with one hidden layer containing 6 units. The first layer weights are initialized from a zero-centered normal distribution with a standard deviation of 0.2, forming connections from 2 input features to the 6 hidden units. The hidden layer biases are initialized to 0, so each hidden unit starts without any initial bias. The output layer is initialized by creating a weight matrix with small random values from a normal distribution and a bias set to 0. The weight matrix connects the hidden units to the single output node, while the bias is a single value. Together, these parameters let the network convert hidden layer activations into final predictions. The model is trained with a learning rate of 0.03, which controls the size of each parameter update and helps balance speed with stability. Training runs for 500 epochs, so the model can improve over repeated passes through the data. A loss history is also recorded to track the mean squared error over time and monitor learning progress. The training loop runs for the chosen number of epochs. During each epoch, the model performs a forward pass by computing the hidden layer values from the inputs, weights, and bias, then applying the hyperbolic tangent activation to add nonlinearity. It then uses these hidden activations with the output weights and bias to produce the final predictions. The code measures prediction error by comparing the model's outputs with the true training targets. It then calculates the mean square error, which summarizes how large those errors are on average and indicates how well the model is performing. The loss value is saved after each training epoch, so performance can be tracked over time. To compute the output layer gradients, first use the number of training samples to average the calculations. The loss gradient is found from the prediction error, scaled and divided by the sample count. Then the output weights are updated using the hidden layer activations and this gradient, while the output biases use the summed gradient across all samples. To backpropagate through the hidden layer, we first find how the loss changes with the layer's pre-activation values. For the hyperbolic tangent activation, this uses the fact that its derivative is 1 minus the activation squared. We then compute the hidden weight gradients by combining the input data with these pre-activation gradients, and compute the hidden bias gradients by summing them across all samples while keeping the correct shape. Gradient descent updates the neural network by adjusting each layer's weights and biases in the direction that reduces error. For both layers, the model subtracts the learning rate times the corresponding gradient from each parameter. Repeating this process helps the network gradually lower the loss and improve its predictions. After training, the model is evaluated on the validation set by passing the validation inputs through the network. The inputs are combined with the first layer's weights and bias, then transformed with the hyperbolic tangent function to create hidden layer activations. These activations are then combined with the second layer's weights and output bias to produce the validation predictions. To evaluate the validation results, we first convert both the actual targets and the model's predictions back to their original units using the same mean and standard deviation from standardization. Then we compute the root mean square error by comparing the restored actual values with the restored predictions. This gives a clear measure of the model's validation error in real-world units. The output reports the NumPy version, the model's starting and ending training loss, and the validation root mean square error in inches. Together, these values show how much the model improved during training and how well it performs on unseen data. If training loss improves a lot, but validation performance remains poor, the model may be overfitting. A Matplotlib figure is created to show how the neural network's training loss changes over epochs. The plot displays the training mean squared error as a navy line with clear axis labels, a descriptive title, and a light grid for readability. Displaying the graph makes it easier to inspect the model's training performance over time. This script uses NumPy to build a small neural network that predicts structural loads from synthetic span and load data with added noise. After standardizing the data, it trains a one hidden layer model with full batch gradient descent to reduce mean squared error. The training loss drops sharply, showing that the model learns the training data, but the higher validation error suggests overfitting. A loss curve and printed results summarize the training progress and highlight the gap between training and validation performance. Loss computation. Loss computation turns a model's predictions into a single measure of error after the forward pass. It compares outputs with the correct answers, rewarding confident correct classifications or measuring distance from true values in regression. This makes performance measurable and provides the basis for gradients used in backpropagation. When computing loss from scratch, make sure each prediction matches the correct target and that their shapes align. After calculating the errors, average them across the batch so the loss stays on a consistent scale. This average loss is then tracked during training to judge whether the model is improving. Loss computation should be numerically stable and match the model's final layer. In classification, raw scores must be turned into probabilities, but this must be done carefully to avoid overflow, underflow, or training failures. A falling training loss shows the model is fitting the training data better, but it does not prove it will generalize to new data. For this reason, loss is both a mathematical objective and a useful signal for monitoring learning. Python code, loss computation. This example shows how to compute loss values for small batches of civil engineering predictions using simple NumPy arrays. These stable loss values provide the basis for later backpropagation. We begin by importing NumPy, a key Python library for numerical computing. It helps work with arrays and mathematical operations efficiently, making it useful for data handling and calculations in the script. A fixed random seed is set with NumPy using the value 7, so the code gives the same results each time it runs. This makes random behavior reproducible, which is helpful for teaching and debugging. The regression targets are the expected settlement values in millimeters. They are stored in a NumPy array, with each value kept in its own subarray, so their dimensions match the model predictions. This format also makes later mathematical operations efficient. The model's predictions are stored in a NumPy array shaped to match the regression targets. This keeps the data consistent and makes it easy to compare predicted values with actual values when evaluating model performance. Before computing errors, the code first checks that the true values and predicted values have matching shapes. This confirms that every true value lines up with the prediction. If they do not match, the data is misaligned and the loss calculation may be incorrect. Mean squared error measures how closely a model's predictions match the true values. It is found by squaring each prediction error and then taking the average, giving a single score for the model's typical squared error. Raw scores for 3 soil classes are stored in a 2-dimensional array, where each row is a sample and each column is a class. This structure organizes the data efficiently for later steps, such as converting scores with softmax or computing loss. We store the correct class index for each sample, so the model's predictions can be compared with the true labels. This lets us find the probability assigned to each correct class and compute the classification loss accurately. Before evaluating classification results, confirm that the number of predictions matches the number of true labels. This means checking that the prediction output has 1 row for each label. This simple validation helps prevent computation errors by ensuring every prediction can be compared with its correct class. To make softmax more numerically stable, shift the logits by subtracting the largest value in each row from every value in that row. This keeps the exponentials from becoming too large, helping prevent overflow and maintain accurate calculations. To convert shifted logits into probabilities, first take the exponential of each value to make the scores easier to normalize. Then divide each exponential score by the total for its row, so the values in each row add up to 1 and represent class probabilities. The probabilities are clipped to stay between a very small positive value and 1 before taking logarithms. This prevents the logarithm of 0 and helps keep later calculations numerically stable. To compute cross-entropy loss, we select the model's predicted probability for the true class of each sample. The correct class labels are used as indices to pull those values from the probability array. These selected probabilities show how much confidence the model assigned to the right answers. Average cross-entropy loss is found by taking the natural log of the predicted probabilities for the correct classes, averaging those log values across the samples, and then making the result negative. This loss measures how well the predicted probabilities match the true labels, with lower values meaning better predictions. We report 3 outputs to evaluate the model. The mean squared error shows the average squared gap between predicted and true settlement values, while cross-entropy shows how well the predicted class probabilities match the true labels. We also display the probability assigned to each correct class, rounded to 3 decimal places, to show the model's confidence. This script uses NumPy arrays to measure model loss for both regression and classification. It calculates mean squared error for predicted versus true settlement values, giving about 14.88 square millimeters. It also computes cross-entropy loss from stabilized class scores converted to probabilities, with an average loss of about 1.303. Finally, it reports the correct class probabilities rounded to 3 decimals to summarize classification performance. Loss computation. Loss computation turns a model's predictions into one error score that guides training. In classification, loss is lower when the model is confident and correct, and higher when it is confident but wrong. In regression, it measures how far predictions are from the true values. When using NumPy, you must carefully match array shapes and format target labels correctly, because the framework will not handle these details automatically. When implementing loss computation from scratch, it is important to consider both the math and numerical stability. For classification, the loss should be low for correct predictions and high for wrong ones. For regression, the loss grows as predictions move farther from the target. In NumPy, losses are usually computed across batches and averaged to give a stable summary of model performance. Accurate loss computation is essential because it drives backpropagation and connects the model's errors to every weight and bias. If the loss is computed incorrectly, the gradients can guide learning in the wrong direction, even when training appears to run normally. Check details such as target encoding and numerical stability, and confirm that loss decreases on simple problems before moving to harder ones. A falling loss usually signals progress, while a flat or unstable loss may point to issues with learning rate, initialization, or preprocessing. Python code. Loss computation. Loss converts model predictions into a single training score. This example contrasts losses for regression and classification and shows that NumPy can be used to compute them from scratch. We begin by importing NumPy, a Python library for numerical computing. It helps work with arrays and mathematical operations, which makes it useful for calculating machine learning losses such as mean squared error and cross-entropy loss. NumPy print settings are adjusted to show numbers with 3 decimal places and avoid scientific notation. This makes results easier to read and interpret, especially in teaching contexts. 2 NumPy arrays are created to compare actual and predicted material strengths in a regression setting. The true strengths are 28, 35, and 42 megapascals, while the predictions are 30, 31, and 45. These paired values will be used to measure prediction error. First, confirm that the true and predicted regression arrays have the same shape. This prevents errors during element-wise calculations and helps ensure the results are valid. An assertion catches any dimension mismatch immediately. To evaluate the regression predictions, we first find the error by comparing each predicted strength with its true value. Then we square those errors and take their average to get the mean square error, a single measure of overall prediction accuracy. The setup defines 3 possible classification categories: safe, review, and unsafe. It then provides predicted probabilities for 2 samples, showing how likely each sample is to belong to each category. The true class labels are also given, with the first sample labeled safe and the second labeled unsafe. These predicted probabilities and true labels can then be compared to compute classification loss. Before using predicted probabilities, verify that they align with the true labels and class names. There should be 1 probability row for each true class label and 1 probability value for each possible class. These checks help prevent indexing errors when selecting the probabilities for the correct classes. To keep logarithm calculations stable, we set a small minimum value called epsilon, so probabilities never reach 0. The NumPy clip function then limits each probability to stay between epsilon and 1. This prevents numerical problems when taking logarithms of very small probabilities. To get the probabilities assigned to the correct classes, create row positions for each example. Then use them together with the true class labels to index the probability array. This selects for every example the model's predicted probability for its actual class. Average cross-entropy classification loss is found by taking the negative logarithm of the predicted probability for each correct class, then averaging those loss values. This gives 1 score for how well the model's predicted probabilities match the true labels. Lower loss means better alignment. The code reports key checks and loss values for both regression and classification. It first shows the NumPy version for reproducibility, then prints the mean squared error to measure regression accuracy. It also shows the model's confidence in the correct classes and the average cross-entropy loss for classification. Overall, lower loss values mean the predictions are closer to the true targets. This script uses NumPy to calculate two common loss measures, mean squared error for regression and cross entropy for classification. The regression loss measures the average squared difference between predicted and true concrete strengths. The classification loss compares predicted probabilities with the correct class labels, using clipping to keep the probabilities stable. In both cases, lower loss values indicate more accurate predictions. Network evaluation. Test performance. Test performance measures how well a neural network works on new data, not just the data it trained on. A model may have low training error because it memorized examples rather than learned useful patterns. Using a separate test set helps reveal whether the model can generalize to unseen cases. Choose test metrics based on the task and the cost of different errors. In classification, accuracy is useful when classes are balanced, but it can hide poor performance when one class is rare, so missed positives and false alarms should be measured separately. In regression, focus on how close predictions are to real values and whether the errors are acceptable for the use case. Overall, test performance should show whether the model is reliable for its intended purpose, not just produce a score. To judge test performance, compare it with training and validation results. Strong training results but weak test results can indicate overfitting, while poor results everywhere may mean the model is too simple or not well trained. A reliable model performs consistently across all datasets, especially when the test set reflects real-world conditions. Python code, test performance. Test performance helps estimate how a network will behave on future data. Using separate data is important because it reveals whether the model has memorized the training set or overfit. In civil applications, evaluation should use realistic unseen cases. The script begins by importing NumPy for efficient numerical work with arrays and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the basic tools for data handling and graphical output. To make random results repeatable, we initialize NumPy's default random number generator with a fixed seed of 7. This produces the same sequence of random numbers each time the code runs, which helps with debugging and comparing results across runs. We create synthetic bridge sensor data by generating 240 sample readings. The values are drawn uniformly between -3 and +3, giving the model a varied set of simulated inputs. Random noise is generated from a normal distribution centered at 0 to represent measurement error or natural variation. This noise is added to a deflection response made from a sine pattern plus a linear trend. The result is a synthetic dataset that resembles noisy real-world sensor readings and can be used to test how well models generalize. Before splitting the data into training and testing sets, the samples are shuffled using a random ordering of their indices. The synthetic bridge sensor measurements and their noisy deflection responses are rearranged in the same order, keeping each input matched with its correct output. This helps remove unintended patterns in the data that could bias model performance. To keep final testing unbiased, the data is split so the model trains only on the earlier samples and tests on later, unseen samples. The training set uses samples up to the chosen training cutoff, while the test set begins at a later point. This separation prevents test data from influencing training and gives a fair measure of model performance. The code first confirms that both the training and testing datasets contain enough samples for meaningful modeling. It then checks that the training inputs and outputs have matching shapes, so each input correctly pairs with its expected output. We compare two polynomial models fitted to the training data, a simple degree 2 model and a much more flexible degree 14 model. The degree 2 model captures a basic quadratic pattern, while the degree 14 model can fit more complex patterns, but is more likely to overfit and perform poorly on new data. We use the fitted, simple, and complex polynomial models to predict responses for both the training and test data. These predictions let us compare how each model performs on data it learned from and on new, unseen data. This is the key step for judging how well each model generalizes. This function computes root mean squared error, a standard measure of prediction accuracy. It compares actual and predicted values by averaging the squared errors, then takes the square root. The result is one value that represents the typical prediction error in the same units as the original data. We first check the NumPy version to support compatibility and reproducibility. Model performance is then evaluated using root mean squared error, or RMSE, measured in millimeters, where lower values are better. The RMSE is calculated and printed for both the simple and complex models on the training and test data, rounded for readability. A much lower training RMSE than test RMSE can indicate overfitting, where a model fits the training data well but does not generalize to new data. This visualization compares how a simple and a complex model perform on unseen test data. A smooth input grid is used to plot each model's predictions across the normalized load sensor range, while the actual test points are shown as a scatter plot. The axes label the sensor readings and bridge deflection in millimeters, and the legend distinguishes the test data from the two model curves. The goal is to show how test performance reveals each model's ability to generalize. This script uses simulated bridge sensor data to show how overfitting affects model performance. It compares a simple quadratic model with a much more complex 14th degree polynomial using training and test data with added noise. The simple model has similar error on both datasets, while the complex model performs well on training data but much worse on test data. This demonstrates that the simpler model generalizes better to unseen measurements. Overfitting signs. Overfitting occurs when a neural network learns the noise and quirks of its training data instead of patterns that generalize to new data. A common sign is high training performance but much lower validation performance. This means the model may appear accurate during training, while failing on unseen examples. So evaluation should focus on how well it performs on data it has not seen before. Overfitting can be spotted by tracking training and validation performance over time. If training loss keeps falling, while validation loss stops improving or rises, the model is learning the training data too closely instead of generalizing. This can happen when a model picks up site-specific patterns, such as artifacts from one hospital's equipment, and then performs poorly in other settings. Overfitting occurs when a model learns training patterns too narrowly, leading to unstable or overly confident predictions on slightly different inputs. It may perform well on familiar images or phrasing, but fail when conditions change. To detect this, evaluation should look beyond accuracy by comparing training and validation performance, reviewing errors, and testing on new data. Python code. Overfitting signs. Use synthetic civil data to show how overfitting appears in a small NumPy neural network. Compare the training and validation loss curves to highlight when the model fits the training data better than it generalizes to new data. The script begins by importing two key libraries, NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these imports prepare the code for data manipulation and plotting. First, we print the NumPy version to confirm the coding environment. This helps with compatibility, debugging, and sharing code, since different NumPy versions can behave or perform differently. A fixed seed is used to make the random number generator produce the same results each time the code runs. Here, the NumPy default random generator is initialized with a seed of 7. This makes the output reproducible, which is helpful in educational settings where learners should see consistent results. We create a small, noisy engineering dataset by generating 80 evenly spaced values from -3 to 3. These values are then shaped into a single column so they are ready for model processing. To simulate a nonlinear settlement response, we add normally distributed random noise centered at 0 to the data, representing real-world variability. The target values are then created from a sign-based pattern combined with a small linear trend and this noise. The result is a realistic nonlinear dataset with randomness, useful for demonstrating overfitting in machine learning models. The dataset is split into training and validation portions. The first 24 samples are used to train the model, while the remaining samples are reserved for validation. This lets the model learn from one part of the data and then be evaluated on unseen data to check how well it generalizes. Before training begins, the code checks that the input and output data have matching sample counts for both training and validation sets. This confirms that every input has a corresponding target value and helps catch data preparation errors before model training starts. The network is set up with one hidden layer containing 40 neurons. Its first layer weights are randomly initialized from a zero-centered normal distribution with a standard deviation of 0.7, while the biases start at 0. This gives the model a basic structure for learning patterns from the input data. The output layer is initialized with weights drawn from a zero-centered normal distribution and a bias set to 0. The weight matrix connects the hidden layer to one output neuron, allowing the network to produce a single prediction. The bias lets the model adjust that prediction independently of the input features. We create 2 lists to record loss values during training, one for the training data and one for the validation data. Tracking both over each epoch helps compare model performance and spot possible overfitting. The model is trained with a learning rate of 0.015 and for 900 epochs. This relatively long training run is meant to give the model enough time to reveal possible overfitting. By comparing performance on the training data with performance on validation data, we can see whether the model is learning patterns that do not generalize well. Gradient descent runs for a fixed number of epochs, repeatedly performing a forward pass through the neural network. The training data is combined with the first weights and bias, then passed through the hyperbolic tangent function to create hidden layer activations. These activations are then combined with the second weights and output bias to produce the model's prediction using the current parameters. To measure training loss for an epoch, compare the model's predictions with the actual training values and calculate the average of the squared errors. This mean squared error shows how well the model is performing, and it is saved so the loss can be tracked over time. To compute the output layer gradients, first find how the loss changes with the predictions by scaling the prediction error by 2 divided by the number of training samples. Then use the hidden layer activations to calculate the weight gradients through a dot product. Finally, get the bias gradients by summing the prediction gradients across all samples while keeping the dimensions consistent. Backpropagation through the hidden layer starts by passing the output layer loss gradient backward through the output weights to measure how the hidden activations affect the loss. This gradient is then adjusted by the derivative of the hyperbolic tangent function, which depends on 1 minus the activation value squared, to account for the hidden layer's pre-activation inputs. Finally, the hidden layer weight gradients are found by combining this result with the training inputs, showing how the weights should change to reduce the loss. During backpropagation, the model computes the first layer's bias gradient by summing the relevant error values while preserving their shape. It then updates the second layer's weights and bias by subtracting the learning rate times their gradients. These adjustments gradually reduce the loss and help the model learn. The code performs a gradient descent update by adjusting the first layer's weights and biases using the learning rate and their gradients. It then uses the updated model to make validation predictions, applying the tan activation in the first layer and the second layer's weights and biases afterward. This lets the model's performance be checked on unseen data. Validation loss is calculated by using the model to predict outputs for the validation data, then comparing those predictions with the true targets. The squared differences are averaged to produce the validation mean squared error. This value is stored so we can track how well the model performs on unseen data over time. The code finds the best validation epoch by using NumPy's RMSE function to locate the lowest validation loss. It then compares the final validation loss with the final training loss. This gap shows how much validation performance differs from training performance, which can help indicate possible overfitting. The overfitting summary reports the epoch with the lowest validation loss, marking the model's best performance on unseen data. It then compares the final training and validation losses, rounded for readability. The difference between them shows the generalization gap, where a larger gap may indicate overfitting. To check for overfitting, we compare when the best validation result occurred with the final training epoch and look at the gap between validation and training loss. If the best epoch was much earlier and the loss gap is large, we warn that validation performance declined while training kept improving, which suggests overfitting. Otherwise, we report that there is no strong overfitting warning for this run. Create a plot of training and validation loss across epochs to compare model learning and generalization. If the validation loss starts to diverge from the training loss, it may indicate overfitting. The plot marks the epoch with the lowest validation loss using a gray-dashed vertical line labeled Best Validation. The x-axis shows training progress by epoch, and the y-axis shows mean squared error. Together, these labels make it easier to compare how training and validation loss change over time. The plot is prepared to highlight overfitting by showing when validation loss begins to rise later in training. A clear title and legend help distinguish the training and validation loss curves, while a tight layout keeps the display readable. Once shown, the graph makes it easier to spot divergence between the curves, which can indicate overfitting. This script shows overfitting with a small, noisy synthetic dataset similar to civil engineering data. A simple neural network is trained until its training loss keeps falling, while validation loss first improves and then rises. This pattern means the model is learning noise in the training data instead of generalizing to new data. The script finds the best validation epoch, checks the gap between training and validation loss, warns when overfitting is likely, and plots the loss curves to show the divergence. Overfitting signs. Overfitting occurs when a neural network memorizes the training data, including noise, instead of learning patterns that work on new data. A key sign is a widening gap between strong training performance and weaker validation or test performance. This matters because high training accuracy alone does not mean the model will succeed in real-world situations with unseen examples. If training and validation performance both improve at first, the model is learning useful patterns. But when training loss keeps falling, while validation loss stops improving or gets worse, the model is likely overfitting. This means it is fitting the training data too closely and may perform poorly on new data, so validation curves should be monitored before deployment. To detect overfitting, compare how a model performs on training, validation, and test data, and examine the errors it makes. If it works well on familiar examples but fails under new conditions, it may have learned patterns that are too narrow. This risk increases with large models, limited data diversity, or training for too long, so evaluation should focus on whether the model truly generalizes. Python code. Overfitting signs. This example indicates overfitting. The model keeps improving on the training data while its validation performance gets worse. The curves show early signs that the model is not generalizing well. We import NumPy for working with arrays and numerical calculations, and Matplotlib's plotting tools for creating visualizations. These common Python libraries are often already available and are widely used for data manipulation and plotting. Printing the NumPy version is a quick way to confirm which release is being used. This helps with compatibility, troubleshooting, and understanding which features are available when sharing or running code. We create reproducible synthetic engineering data by using a fixed random seed, so the same random values are produced each time the code runs. Then we generate 90 evenly spaced inputs from -3 to +3 and reshape them into a column format. This provides a consistent dataset for testing a range of input conditions. The true settlement data is created from a smooth pattern that combines a sine function with a linear trend. Random noise from a normal distribution with mean 0 and standard deviation 0.18 is then added to simulate real measurement error. This makes the data more realistic and harder for a model to fit perfectly. To simulate real-world data, measurement noise is added to the true signal, producing noisy observations. The input data and noisy output are then checked to make sure their shapes match, which keeps later processing and analysis consistent. To encourage overfitting, we train on only a small subset of the data by selecting every third point. The validation set is then made from all remaining points, so it contains data the model did not see during training. This lets us compare training performance with performance on unseen data. The training set is created by selecting the same indexed rows from the full input data and the full target data. This gives matching features and labels, so the model is trained on a consistent subset of the dataset. Keep validation data separate from training by selecting the reserved validation inputs and their matching outputs from the full dataset. This prevents the model from learning from those examples during training. Evaluating on this unseen data gives a clearer measure of generalization and helps reveal overfitting. This function calculates mean squared error, a common way to measure prediction accuracy. It compares actual and predicted values, squares the differences so they are all positive, and averages them into one number. A lower mean squared error means the model's predictions are closer to the actual data. We compare polynomial models of degree 3 and 18 to contrast a simpler model with a more complex one and observe possible overfitting. An empty results collection is prepared to store each model's degree, training loss, validation loss, and predictions, so the models can be fitted and evaluated consistently. For each polynomial degree, we create matching polynomial features for both the training and validation data. The training features are used to fit the polynomial model, while the validation features prepare the data for evaluating how well that model performs. We use NumPy's least squares method to find the polynomial weights that best fit the training data, using basic linear algebra rather than a machine learning library. Then we measure training loss with mean squared error by comparing the true training values to the model's predictions. We do the same on the validation data to see how well the model performs on unseen examples. For each polynomial degree, the data is transformed into polynomial features and used with the learned weights to make predictions across the dataset. The degree, training loss, validation loss, and predictions are then saved so different polynomial models can be compared and visualized later. The code compares training and validation performance for each polynomial degree by reporting their mean squared errors and the difference between them. A larger validation error compared with the training error signals a bigger performance gap, which can indicate overfitting. A key warning sign of overfitting is low training error paired with much higher validation error. This means the model may be fitting the training data too closely, including noise, and may not generalize well to new data. Set up a plotting canvas. Then display the training and validation data as separate scatter plots. The training points are shown with a clear label and larger size, while the validation points are smaller and slightly transparent so the two datasets are easy to distinguish. Next, we add the model curves to the plot by using each polynomial degree's predictions and plotting them against the full set of x values. Each curve is labeled by its degree, making it easier to compare how well the different models fit the data. The plot is labeled to make its message clear. Validation performance is lagging, which suggests overfitting. The horizontal axis shows soil depth position in meters, and the vertical axis shows settlement readings in centimeters. Together, the title and axis labels help viewers understand both the data and the overfitting issue. To finish the plot, we add a legend to identify the data and model fits, turn on a subtle grid for readability, and adjust the layout so everything fits cleanly. Displaying the plot then lets us compare the fits visually and look for possible overfitting. This script shows overfitting by fitting low-degree and high-degree polynomial models to noisy sign-based data. The high-degree model achieves much lower training error, but its validation error rises, showing that it has learned the training points too closely instead of generalizing. The printed mean squared errors and plotted curves highlight this gap, with the complex model fitting the training data well, but performing poorly on validation data. In this lecture, you learn to explain gradient descent, stochastic gradient descent, and backpropagation at an intuitive level. Implement a small neural network training loop from scratch using NumPy, and evaluate neural network performance and identify signs of overfitting. In the next module, Module 8, we will go over none. Thank you for your attention. See you all in the next lecture.